Welcome to the TM chapter of the HT32 MCU basic tutorial. This tutorial will introduce to you the HT32 MCU TM function. We will introduce this function from four aspects: TM overview, TM basic function, TM application introduction, and TM library and application example. TM overview. The TM, which stands for Timer Module, is an important peripheral in the HT32 MCU and appears in almost every application. From simple LED flashing control to complex motor speed regulation, timers provide an accurate time management mechanism, enabling users to implement various functions such as timer, counter, PWM generation, input capture and output compare. We will introduce four timers: SCTM, PWM, GPTM and MCTM. The number of these four timers in the HT32F52352 and HT32F50230 MCUs is listed on the right. The following table shows the main differences between these four timers. The SCTM has one input channel and one output channel. It only supports the up-counting mode. The PWM has four output channels but no input channel. It supports both up-counting and down-counting modes. The GPTM has four input channels and four output channels. It supports both up-counting and down-counting modes. The MCTM has four input channels and four output channels. It supports both up-counting and down-counting modes. It also has a break function and a complementary output function. Next, we'll introduce the timer features. Here takes the GPTM as an example. For other timer modules, refer to the corresponding user manual. The GPTM has a 16-bit up or down auto-reload counter that enables up-counting, down-counting and center-aligned counting, that is, both up-counting and down-counting. A 16-bit programmable prescaler allows the input clock to be divided by any factor between 1 and 65,536. For the SCTM, it has a 16-bit up auto-reload counter that can only enable up-counting. The GPTM has four independent channels for input capture, compare match output, generation of PWM waveform and single pulse mode output. The SCTM only has one input and output channel. The PWM does not have an input channel. In the input capture mode, the TM can capture the rising or falling edge of an input signal. In the compare match output mode, the counter value matches the contents of the CHX-CCR register, thereby performing operations such as setting the output to 1 or clearing the output to 0, or toggling the output. In the PWM mode, a PWM waveform with a specific frequency and duty cycle can be output under the compare match output. In the single pulse mode, after receiving a trigger signal, a pulse signal with a specific delay and pulse width will be generated, and then the counting will stop. The GPTM supports an encoder interface controller with two inputs using a quadrature decoder. The SCTM, PWM and MCTM do not have the quadrature decoder. However, the MCTM supports three-phase motor control and Hall sensor interface. The GPTM and MCTM can be internally connected together for timer synchronization. The GPTM can generate an interrupt or PDMA when one of the following events occurs: an update event, a trigger event, an input capture event, or an output compare match event. For the MCTM, in addition to these events, it can also generate an interrupt or PDMA when an update event 1, an update event 2, or a break event occurs, while a break event occurrence only generates an interrupt. For the MCTM, in addition to these features, it has a repetition counter, a break function, and a complementary output function. The timer structure can generally be divided into 5 parts. The clock source, the count control, the input control, the output control, and the capture or compare register. Some timers, such as the PWM, do not have the input control and capture register. They only have the compare register. We will take the GPTM as an example to introduce these parts. The clock source can be the internal clock source, that is, the internal APB clock FCLKIN, or generated by triggering the edge of the STI input source, STIED. In addition to these, the GPTM clock source can also be generated using a quadrature decoder. The count control consists of 3 parts. The prescaler PSC, the counter TM-CNT, and the reload register CRR. The MCTM also has a repetition counter. The input control consists of a digital filter, a channel polarity selection, edge detection, and a channel prescaler. The capture or compare register is used for selecting capture input or comparing match output. The output control is used for compare match, single pulse or PWM output function. TM basic function. The timer clock source is used to drive the counter prescaler. The default internal clock source is the APB clock FCLKIN, used to drive the counter prescaler. The counter prescaler can count during each rising edge of the STI signal. When the STI signal is selected as the clock source, the internal edge detection circuitry will generate a clock pulse during each STI signal rising edge to drive the counter prescaler. This mode can be selected by setting the SMSEL field to hex 7 in the MDCFR register. The trigger input source can be selected by setting the TRSEL field. There are various types of trigger input source. Here, we take the GPTM as an example. These include software trigger by setting the UEVG bit. Filter input of channel 0, TI0S0. Filter input of channel 1, TI1S1. Channel 0 edge detector, TI0BED. Internal timing module trigger 0, ITI0. Internal timing module trigger 1, ITI1. And internal timing module trigger 2, ITI2. It is important to note that if the TRSEL field is set to hex 0 to select the software UEVG bit as the trigger source, then when the SMSEL field is set to hex 7, the counter will be updated instead of counting. Only the GPTM has the quadrature decoder. To select quadrature decoder mode, the SMSEL field should be set to hex 1, hex 2, or hex 3 in the MDCFR register. The quadrature decoder function uses 2 input states of the GTCH0 and GTCH1 pins to generate the clock pulse to drive the counter prescaler. The counting direction bit DIR is modified by hardware automatically at each transition on the input source signal. The input source signal can be derived from the GTCH0 pin only, the GTCH1 pin only, or both GTCH0 and GTCH1 pins. Then, go on to the prescaler and counter. The counter in different timers is different. We will take the GPTM as an example. The prescaler has 1 input clock and 1 output clock. The input clock is the clock source output, while the output clock drives the counter. The clock is divided by setting the PSCV value, which ranges from 0 to 65,535, to achieve division by 1 to 65,536. A 16-bit up or down counter enables up counting, down counting, and center-aligned counting. The counter value can be up to 65,535. The SCTM has a 16-bit up counter that can only enable up counting. Then we will introduce the reload register CRR, the repetition counter REPR, and counting modes. First, let's introduce the reload register and the repetition counter. The reload register is a 16-bit register that specifies the counter reload value CRV, which represents the maximum value that the counter can count to. Only the MCTM has a repetition counter. It is an 8-bit counter. The update event 1 is usually generated at each overflow or underflow event occurrence. When the repetition operation is active by assigning a non-zero value into the REPR register, the update event is only generated if the REPR counter has reached 0. Next, we will introduce the counting modes. There are 3 modes: up counting, down counting, and center-aligned counting. In the up counting mode, the counter continuously counts up from 0 to the counter reload value, which is defined in the CRR register, then restarts to count from 0 and generates an overflow event. This action will continue repeatedly. In the down counting mode, the counter continuously counts down from the counter reload value, which is defined in the CRR register, to 0, then restarts to count from the counter reload value and generates an underflow event. This action will continue repeatedly. In the center-aligned counting mode, the counter counts up from 0 to the counter reload value, and then counts down to 0 alternatively. The timer module generates an overflow event when the counter counts to the counter reload value in the up counting mode and generates an underflow event when the counter counts to 0 in the down counting mode. The count direction is updated by hardware automatically. We will take the GPTM timer as an example to introduce the input control. The input control consists of a digital filter, a channel polarity selection, edge detection circuits, and a channel prescaler. The GPTM timer has 4 independent channels. Here, we will only introduce channel 0 and channel 1. Channel 2 and channel 3 are similar and will not be introduced. The channel 0 input signal TI0 can be chosen to come from the GTCH0 signal or the exclusive or function of the GTCH0, GTCH1 and GTCH2 signals. The channel 1 input signal TI1 is from the GTCH1 signal. The channel input signal TIX is sampled by a digital filter to generate a filtered input signal, TIXFP, where X can be 0 or 1. Now, let's take a look at the top section. The filtered input signal TI0FP passes through 2 edge detectors to generate an edge detection signal TI0BED. Then the filtered input signal TIXFP passes through a channel polarity to obtain a TIXSX signal, then passes through an edge detector to generate a single edge detection signal TIXSXED. The TIXSXED signal can be used for input capture function. The CHXP bit in the CHP-OLR register determines whether the capture event occurs on a channel rising or falling edge. The CHX-CCS bits determine whether the channel capture is from the TIXSXED or TRCED signal. The TRCED signal is generated by the TI0BED, ITI0, ITI1 and ITI2 via the trigger controller. The effective input event number can be set by the channel capture input source prescaler setting field CHXPSC, that is, a channel capture input signal is generated every n effective events. Here, n can be set to 1, 2, 4, or 8. We will take the GPTM timer as an example to introduce the output control. The output control consists of an output mode controller, a channel polarity selection and a channel controller. The CHXOM field in the CHXOCFR register define the output reference signal CH0OREF. When the counter value matches the contents of the CHXCCR register, the CHXOREF output can be configured for various functional types, including no change, low level, high level, toggle, PWM mode 1, and PWM mode 2. The CHXOREF signal can be configured as either active high or active low via the channel polarity selection. Finally, a channel output signal CHXO can be generated via the channel controller. The timer capture or compare register can be used for input capture and compare match output functions. The SCTM only has one channel. The PWM does not have the input capture function. The GPTM and MCTM are basically the same. Here, we will take the GPTM timer as an example. Each capture input or compare match output channel is composed of a preload register and a shadow register. Data access of the APB bus is always implemented by reading or writing the preload register. When used in the input capture mode, the counter value is captured into the CHX-CCR shadow register first and then transferred into the CHX-CCR preload register when the capture event occurs. When used in the compare match output mode, the contents of the CHX-CCR preload register is copied into the associated shadow register. The counter value is then compared with the register value. Then, we'll introduce the trigger controller. The trigger controller is used to select the trigger source and set up the trigger level or edge trigger condition. As mentioned above, the trigger input sources include software trigger by setting the UEVG bit, filter input of channel 0, TI0S0. Filter input of channel 1, TI1S1. Channel 0 edge detector, TI0BED. Internal timing module trigger 0, ITI0. Internal timing module trigger 1, ITI1. And internal timing module trigger 2, ITI2. The trigger level condition depends on the input signal high and low level. Therefore, the STI level trigger source can be the UEV1G bit, TI0S0, TI1S1, ITI0, ITI1, or ITI2. However, the channel 0 edge detector TI0BED is generated by TI0 passing through the edge detector and does not have a high or low state. Therefore, it cannot be used as an STI level trigger source. The edge trigger condition depends on the rising or falling edge of an input signal. Therefore, the STI-ED edge trigger source can be the TI0S0ED, TI1S1ED, ITI0ED, ITI1ED, or ITI2ED. Similarly, as the UEV1G bit does not have an edge change, it cannot be used as an STI-ED edge trigger source. The TM can be synchronized with an external trigger in several modes, including the restart mode, the pause mode. The trigger input of these modes comes from the STI signal, which is selected by the TRSEL field in the TRCFR register. In the restart mode, the counter and its prescaler can be reinitialized in response to a rising edge of the STI signal. When an STI rising edge occurs, the update event software generation bit named UEVG will automatically be asserted by hardware, and the trigger event flag will also be set. Then the counter and prescaler will be reinitialized. In the pause mode, the selected STI input signal level is used to control the counter start or stop operation. Note that since the pause function depends upon the STI level to control the counter stop or start operation, the selected STI trigger signal cannot be derived from the edge detector TI0BED signal. In the trigger mode, after the counter is disabled to count, the counter can resume counting when an STI rising edge signal occurs. Note that if the STI signal is selected to be derived from the UEVG bit software trigger, the counter will not resume counting. When software triggering using the UEVG bit is selected as the STI source signal, there will be no clock pulse generated which can be used to make the counter resume counting. The PWM, GPTM, and MCTM can be internally connected together for timer chaining or synchronization. This can be implemented by configuring one timer to operate in the master mode, while configuring another timer to be in the slave mode. On the right are the internal trigger connection tables for the HT32F52352 and the HT32F50230. The diagram on the left shows the timer synchronization of the HT32F52352 GPTM. When one GPTM is configured to be in the master mode, the master controller will generate a master trigger output signal MTO which can be used as an internal trigger input ITI. This signal can trigger or drive a reset, a start or a stop for the GPTM or MCTM in slave mode, or provide a clock source for it. Then, we'll briefly introduce the TM-related registers. The timer counter configuration register specifies the timer counter configuration. The timer mode configuration register specifies the timer master and slave mode selection and single pulse mode. The timer trigger configuration register specifies the trigger source selection of the timer. The timer control register specifies the timer enable bit and CRR buffer enable bit. The channel X input configuration register specifies the channel X input mode configuration. The channel X output configuration register specifies the channel X output mode configuration. The channel control register contains the channel capture input or compare output function enable control bits. The channel polarity configuration register contains the channel capture input or compare output polarity control. The timer interrupt control register contains the timer interrupt enable control bits. The timer event generator register contains the software event generator bits. The timer interrupt status register stores the timer interrupt status. The timer counter register stores the timer counter value. The timer prescaler register specifies the timer prescaler value to generate the counter clock. The timer counter reload register specifies the timer counter reload value. The channel X capture or compare register specifies the timer channel X capture or compare value. The channel X asymmetric compare register specifies the timer channel X asymmetric compare value. The channel X compare register specifies the PWM timer channel X compare value. The channel break configuration register specifies the channel output idle state when the MCTM uses the break function. The channel break control register specifies the MCTM channel break control bits. The timer repetition register specifies the MCTM timer repetition counter value. TM application introduction. The input capture function can capture either the rising or falling edge of an input signal. It is commonly used for pulse width measurement and pulse counting. The following will introduce pulse width measurement. A capture event on both the rising or falling edge of an input signal can be triggered by configuring the input capture channel. The values of the counter at the time of these two events are recorded, and the difference multiplied by the counter cycle time of the timer is the pulse width. The figure on the right shows the pulse width measurement process. 1. Use one input channel CH1 with one capture channel initially set to capture on the rising edge. 2. When the capture channel detects a rising edge, the counter value is captured into the CH1 CCR register, named as value 1. In the capture event interrupt service function, switch the capture channel polarity so that the timer can capture on the falling edge. 3. When the capture channel detects a falling edge, the counter value is captured into the CH1 CCR register, named as value 2. 4. If an overflow occurs during either of the two capture processes, the number of overflows N must also be included in the calculation. Therefore, the calculation formula for pulse width W is as shown above. There are up to 10 types of compare output, which are configured by the channel output configuration register. Then, we'll briefly introduce the commonly used PWM output square wave. Refer to the user manual for other types. PWM output square wave is a square wave signal with an adjustable duty cycle that can be output by configuring the capture or compare register CCR and the reload register CRR. The three main parameters are resolution, frequency, and duty cycle. Resolution is the number of levels at which the duty cycle of the PWM square wave signal can be adjusted. It is inversely proportional to the frequency. In other words, the higher the resolution, the lower the frequency. Frequency is the number of times that the PWM square wave signal repeats within a unit of time. The calculation formula is shown above, where FCK-PST is the clock frequency of the clock source, PSCV is the prescaler value, and CRR is the reload register value. Duty cycle is the proportion of high-level signals in the PWM square wave signal. The following functions are only supported by the MCTM: complementary output, dead time, and break function. The channel X output reference signal CHXOREF is defined by the CHXOM bit in the channel X output configuration register CHXOCFR. When the counter value matches the contents of the CHXCCR register, the CHXOREF output can be configured for various functional types, including no change, low level, high level, toggle, PWM mode 1, and PWM mode 2. The channel X output reference signal CHXOREF passes through the dead time generator DTG, and then the polarity selection which configures the channel output as either high level or low level active. Finally, the channel controller generates a pair of complementary channel output signals, CHXO and CHXNO, with dead time delay. The CHXO signal is the same as the CHXOREF signal except for the rising edge which is delayed with a dead time relative to the reference signal rising edge. The CHXNO is the opposite of the CHXOREF signal except for the rising edge, which is delayed with a dead time relative to the reference signal falling edge. The MCTM includes break function and one input signal for MCTM break, MTBRK. The MTBRK is default function and from external MTBRK pin. When the MTBRK input has an active level or the clock monitor circuitry detects a clock failure event, a break event will be generated if the break function is enabled. Meanwhile, each channel output will be forced to a reset state, an inactive or idle state. Moreover, a break event can also be generated by the software asserting the BRKG bit in the EVGR register even if the break function is disabled. The GPTM has a quadrature decoder. The quadrature decoder function uses two quadrantal inputs TI0 and TI1 derived from the GTCH0 and GTCH1 pins respectively to interact to generate the counter value. The DIR bit is modified by hardware automatically during each input source transition. The input source can be either TI0 only, TI1 only, or both TI0 and TI1, the selection made by setting the SMSEL field to hex 1, hex 2, or hex 3. On the left is an example of both TI0 and TI1 quadrature decoder counting. The counting direction and encoding signals are shown on the right. Here is a brief explanation. Initially, TI0 is a rising edge and TI1 is at a low level. As shown in the figure, the counter value increases. Next, TI0 is at a high level and TI1 is a rising edge. As shown in the figure, the counter value increases again. The rest of the process is the same, so it is not introduced here. TM library and application example. Holtec provides a standard peripheral firmware library including macros, functions, and examples for peripherals. Using this library does not require users to have advanced knowledge of the HT32 MCU peripheral specifications, thus significantly reducing development costs. We have categorized timer-related functions as follows. These categories will be introduced briefly below. The initialization-related APIs are the functions used to initialize TM content. The trigger source and clock-related APIs are the functions used to configure the timer trigger source and clock. The counter-related APIs are the functions used for timer counter operations. The quadrature decoder or Hall sensor-related APIs are the function used to configure the quadrature decoder or Hall sensor. The output configuration APIs are the functions used to configure timer output operations. The input configuration APIs are the functions used to configure timer input operations. The mode configuration related APIs are the functions used to configure timer master and slave mode, and single pulse mode. The channel polarity or channel control related APIs are the functions used to configure the input or output channel polarity and channel enable or disable. The interrupt PDMA event configuration related APIs are the functions used to configure the interrupt PDMA various events and corresponding flags. The channel capture or compare register configuration related APIs are the functions used for channel capture or compare register operations. Finally, we will provide two application examples to summarize this tutorial. The example 1 is one of the standard peripheral firmware library examples. It should be used with the hardware starter. The main program is as follows. After PWM initialization, the program will set the PWM duty cycle and then enable the PWM. A PWM square wave with the specified frequency and duty cycle is then output. Then, adjust the duty cycle and disable the PWM. It can then be seen that the PWM duty cycle has changed. Finally, adjust the PWM frequency and duty cycle, and re-enable the PWM to output a PWM square wave with the adjusted frequency and duty cycle. Here are critical codes of this example. In the main program, first execute the PWM init function to initialize the PWM. Then, set the duty cycle of the PWM output square wave to 50% for channel 0 and 25% for channel 1. Then, enable the PWM. Next, adjust the duty cycle of the PWM output square wave by setting it to 0% for channel 0 and 75% for channel 1. Then, disable the PWM. Finally, set the frequency of the PWM output square wave to 12 kHz, and set the duty cycle to 25% for channel 0 and 75% for channel 1. These are the main configurations of the PWM init function. First, perform the timer basic configuration, set the clock prescaler, reload value, repetition counter value, and counting mode in sequence. Then, enable the prescaler preload and reload register preload functions, and clear the update event interrupt flag. Next, configure the TM output channel. Set the PWM mode 1, channel enable, complementary channel disable. Channel polarity, complementary channel polarity, channel idle state, complementary channel idle state. Compare value, and asymmetric compare value. Finally, configure channel 0 and channel 1 as the PWM output channels. The example 2 is one of the standard peripheral firmware library examples. It should be used with the hardware starter. The program functionality is divided into two parts: the main program and the interrupt service routine. In this example, a capture channel of input channel CH1 in the HT32 F52352 GPTM is used for pulse width measurement. First, the main program executes the timer basic configuration, and sets the timer capture channel configuration. It then enables the capture event interrupt, and update event interrupt, then enables the timer. Finally, it executes the capture main routine in a loop. The pulse width can be viewed via the serial port. In the interrupt service routine, the number of counter overflows, and the CH1 CCR value on the rising or falling edge are obtained by generating the update event interrupt, and capture event interrupt continuously. Then, the counter value is obtained through the capture process. Finally, switch the channel polarity to obtain the pulse width. Here are critical codes of this example. These are the main configurations for the timer in the main program. First, perform the timer basic configuration. Set the clock prescaler, reload value, repetition counter value, and counting mode in sequence. Then, enable the prescaler preload function and clear the update event interrupt flag. Next, configure the timer capture channel. Set the capture channel, channel polarity, channel capture selection, capture input source prescaler, and channel input source filter in sequence. Finally, enable the timer capture event interrupt and update event interrupt, then enable the timer. The HTCFG-CAP-IRQ handler is an interrupt service routine. The capture event interrupt and the update event interrupt are executed within this function. First, set the status and CN variables to store and clear the interrupt flags. When an update event interrupt occurs, the overflow count increments by 1, enabling the overflow count to be obtained directly. When a capture event interrupt occurs, the CH1CCR value on the current rising or falling edge is obtained, and the counter value is obtained via the capture process. Finally, switch the channel polarity. The above is the calculation process for obtaining the counter value in the capture process. Overflow counter n multiplied by the sum of the reload value CRR and 1. Minus the CH1CCR value obtained on the rising edge and plus the CH1CCR value obtained on the falling edge. The following is the capture main routine. It prints the counter value and pulse width via the serial port. Taking the HT32 F52352 as an example, the system clock is set to 48 MHz by default and the prescaler value is set to 0. Therefore, the pulse width W can be calculated as follows. W is equal to dividing 1 by 48 MHz and multiplying by the counter value obtained in the capture process. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.